And today we're happy to have Ilia Itenberg with the talk about empty real plane sextic curves.
Thank you very much. And thank you very much for the invitation to give a talk in the seminar. Just to make sure, so it's 1 hour for the talk?
No, actually, it's not time bound. So it's up to you. It can go longer than 1 hour.
That's extremely dangerous.
Oh.
Okay. So indeed, I'd like to speak today about what one can call empty real sextics, and so this is a subject that belongs to topology of real algebraic curves, and in a sense, it's the framework of Hilbert's 16th problem, or more precisely, the first part of Hilbert's 16th problem. So, let me first discuss a little bit this first part of Hilbert's 16th problem before coming to discussion of empty real sextics. So, what are these questions Hilbert put in the first part of his 16th problem? So you take homogeneous real polynomial of degree d in 3 variables, and so such polynomial f has 0 locus in the real projective plane. It also has 0 locus in the complex projective plane. So you have a kind of commutative diagram like this. So if you assume that the curve you are considering is non-singular, meaning that this polynomial f does not have critical points outside of the origin in C3, so I'm excluding not just real singularities, but also complex singularities. So if we assume that we are dealing with a non-singular curve, so the complex point set is a Riemann surface in CP2, and since the coefficients of our polynomial are real, the complex conjugation acting in CP2 restricts to an involution on our Riemann surface, and the real point set of our curve is the fixed point set of this involution, and we are interested in the topology of this real point set. So what does it mean, topology? Since we are speaking about non-singular curve, so this 0 locus of our polynomial in the real projective plane is a collection of circles somehow embedded in RP2, and we can be interested in the topology of this real point set itself, or we can be interested, which is a much more interesting question, we can be interested in the topology of this topological pair RP2 RF, so RP2 and the real point set of our curve. So we can ask what kind of picture can we see in RP2 if we draw this 0 locus of our polynomial in the real projective plane, provided that the degree is d, so the degree is fixed. And the first non-trivial case is the case of degree 6. So we'll come to degree 6 in a couple of minutes. But let's first discuss the question concerning the topology of the real point set of our curve, the real point set itself, without considering the embedding of this real point set in RP2. So since it's a collection of circles, the topology of this collection of circles is determined by the number of the circles. And for this number, there is an inequality called Harnack inequality. So the number of connected components of the real point set of our curve, I don't know why did I wrote x, so it's f. So the number of connected components of this real point zero locus of our polynomial in AP2 is bounded from above by d minus 1 times d minus 2 over 2 plus 1. So d minus 1 plus d minus 2, d minus 1 times d minus 2 over 2 is the genus of this Riemann surface, which is the complex point set of our curve. And so this the bound is genus plus 1. And Harnack, in fact, not only proved this inequality, but he also proved that this upper bound is sharp in any degree. And so this is what is called maximal curves. So we say that a curve is maximal if the number of connected components of the real point set of this curve is equal to d minus 1 times d minus 2 over 2 plus 1. And so in principle, it's not difficult to understand that it gives a topological classification of non-singular curves of given degree in AP2, because the number of connected components is bounded from above by this genus plus 1, according to Harnack inequality. And of course, you have a lower bound. So this number is bounded from below by 0, and even better. So if the degree is odd, then you can bound from below the number of components by 1, and of course 0 and 1. So 0 in the case of even degree and 1 in the case of odd degree. This low bounds are sharp. And since you have a sharp lower bound and a sharp upper bound, in fact, you have a complete topological classification, because since you know that this minimal value and maximal value are realizable, all the intermediate values are also realizable. You can easily prove it just walking in the space of all curves of given degree. So the question about the topology of the real point set of a non-singular curve of given degree in AP2. So this question was settled by Harnack. By the way, it's 1876. But as I said, much more difficult question is a question about the topology of this topological pair AP2 RF, where RF is the zero locus of a polynomial of given degree D, and we assume that the curves we are considering are non-singular. And so this question was included by Hilbert in the first part of his sextant problem. And this question is indeed much more difficult. The answer is known only up to degree 7. One can hope that the classification of these topological pairs will be completed in degree 8, probably at some moment in degree 9, but it looks like general questions or general classification for an arbitrary degree is really hopeless. And as I said, the first non-trivial case is the case of degree 6. And so let me show you this isotopy, or just another adjective to describe this classification of topological pairs. In the case of maximal non-singular sextics, so according to the Harnack inequality, in the case of sextics, in the case of curves of degree 6, the number of connected components, the maximal possible number of connected components of the real point set is 11. And it turns out that there are only 3 possible topological pairs that can be realized by maximal non-singular sextics. So there is, well, first of all, what I am drawing on these pictures So if you consider just one circle embedded in AP2, so you have like two different topological ways to embed a circle in AP2. It can be embedded like a circle, meaning that the circle divides AP2 into parts. One part is, okay, let me draw something. So it can be like this. So such a circle divides AP2 into parts. One part is homeomorphic to a disk, and the other part is Möbius band. And the second option is to embed a circle like a line. So in this case, the complement of the circle is connected. And it's not difficult to understand that if we are dealing with non-singular curves of even degree, then all the connected components of the real point set are embedded like circles, what they call ovals. So this terminology with ovals has nothing to do with any notion of convexity. So an oval can be can have a complicated shape, but oval just means a circle embedded in AP2 in such a way that the complement has two connected components. And so if the degree is even and our curve is non-singular, then all the connected components are ovals. And so what is drawn in the first picture, in this picture of a Harnack curve. So we have one oval, then another oval inside meaning in this connected component, which is homomorphic to the disk, and 9 ovals outside. So this topology was realized by Harnack himself. So when he proved that his estimate, his upper bound is sharp, he constructed a family of curves, in particular in degree 6, he constructed a curve with such a topology. Then Hilbert succeeded to construct another curve, so to realize another topology. So here he constructed a maximal sextic with one oval having 9 ovals inside and 1 oval outside. And Hilbert even conjectured that these two options, the Harnack one and the one Hilbert constructed, were the only possible options for maximal non-singular sextics. But it turns out that there is the third one. Such a curve was constructed by Gutkov, and this curve, Gutkov's curve, has 5 ovals inside one oval and 5 ovals outside. And there are no other possibilities. So this is a complete classification, isotopic classification of maximal non-singular sextics. So a lot of things are known about sextic curves. So in particular, for sextics, there is not only an isotopic classification, but also what is called rigid isotopic classification. So what is rigid isotopic classification? So in the case of non-singular sextics, this expression, rigid isotopic classification, means the following. So you consider the space of all sextic curves, all curves of degree 6 in AP2, so singular and non-singular. So this space can be naturally seen as a real projective space. And this real projective space, there is the discriminant whose points correspond to singular sextics. And the rigid isotopic classification is a description of connected components of the complement of the discriminants. So we say that two non-singular sextic curves in AP2 are rigidly isotopic if the corresponding points in the space of all sextics are in the same connected component of the complement of the discriminant. And so such a rigid isotopic classification of non-singular sextics was obtained by Nikulin. In the case of sextics with one non-degenerate double point, so of course you can adjust the notion of rigid isotopy in the case of singular curves, but you can easily guess how to define rigid isotopes in the case of sextics with one non-degenerate double point. So such rigid isotopic classification I obtained a number of years ago. So, and in both cases, in the case of non-singular sextics and in the case of sextics with one non-degenerate double point, these rigid isotopic classifications were obtained due to the fact that plane sextic curves are directly related with the K3 surfaces, and one can use the standard machinery of K3 surfaces. One can apply this machinery to this problem of rigid isotopic classification. This machinery can also be applied to study complex sextics, of course. So it's not very interesting to classify complex sextic curves up to non-singular complex sextic curves up to rigid isotopy, because the complement of the discriminant in the space of complex sextic curves, the complement is connected, but one can study singular complex sextics. So one can study complex sextics, singular complex sextics up to equisingular deformations, and this was done by Degtyarev and Degtyarev, once again using the machinery of K3 surfaces. And an impression after all this works was that this machinery of K3 surfaces can be applied either in the complex situation. In this case, one can study singular objects, or in the real situation, but in this case, the objects should be either non-singular, like in Nikulin's case, or almost non-singular, like in the case of real sextics with one non-degenerate double point. So the impression was that it's difficult to apply this machinery when one tries to combine real and singular. But in fact, it turns out that there is at least one situation where one can use this K3 machinery to study real singular curves, real singular sextics, and this is the case of what one should probably call empty real sextics. So that's exactly what I like to discuss today. So what do I mean by empty real plane curves? So of course the expression is not very good, but empty means with empty real path. So once again, a real object for me is a complex object equipped with an anti-holomorphic convolution, and so we can consider real sextic curves such that the real path, so the zero locus of polynomials we consider zero locus in AP2 is empty. I will call this curves empty. Of course, you can play this game in any even degree. So if you want to have an empty real plane curve, the degree should be even. And then you can try to look for kind of classification of this empty real curves in given degree. And once again, the degree 6 is the first interesting degree, the first non-trivial case, because if the degree is 2, then so empty real conics are necessarily non-singular, and they are all equivariant deformation equivalent. So this is a general observation that if you're interested in empty non-singular real curves, then for given degree, all these curves are rigidly isotopic, are equivariantly deformation equivalent. You can just consider the corresponding points in the space of curves of given degree, and you can connect these curves by a segment, and you can follow this segment. Probably you will need to perturb a little bit this this path to avoid complex singularities, but in a sense you can go straight from one point to another. You will not get real singularities, and as I said, perturbing this path you can avoid complex singularities. So in the case of degree 2, everything is simple. In the case of degree 4, things are a little bit more complicated, but still simple. So here is the complete list of options. So what do I mean by options? I describe possible singularities, and in fact, I also at the same time describe equivariant equisingular deformation classification. So empty real quartic can be either non-singular, or it can have two non-generate double points. This, I will just write 2A1. It can happen that this quartic has 4 non-generate double points. So in this case, the quartic is necessarily reducible, and there are 2 deformation families. So our quartic is union of 2 conics, and these conics are either real or complex conjugate. So it can happen that you have 2 cusps, and you can have 2 tangency points, or 2 points of type A3. In this case, once again, the quartic is reducible, and once again, there are 2 families, 2 deformation families. So everything is very elementary. And what I'd like to present today, it's our joint work with Alex Degtyarev. So what we obtained, so we obtained an equivariant equisingular deformation classification of empty real sextics. So as I said, we use this approach based on the K3 machinery, and so let me try to describe this this approach. So first of all, let me introduce some notions before I formulate the theorem. So in fact, you will see the statement of the theorem is strange, because I decided just to present numbers of classes and not a complete description of these classes, because there are many of them. But I will try to explain how this classification, well, I will not be able to show you how this classification looks like, but I will try to explain how this classification is formulated, at least. So first of all, I need the notion of lattice type. So we will be interested in just to use this K3 machinery. I need an additional assumption. So I will assume that we are working with a simple sextic. So simple means that the singularities, so means that our sextic is reduced, and the singularities are simple. meaning of ADE type. In fact, it's of course a restriction, but it's not a very serious restriction. So of course one can deal easily with the case of non-reduced empty sextics, and one can easily deal with the case of reduced non-simple sextics. I will mention this remark a little bit later. But let's assume that our sextic is simple, so all the singularities are of ADE type. And then, so what we can do, we can consider the double covering of the complex projective plane ramified along the complex point set of our sextic, and we can take the minimal resolution of this double covering. And this minimal resolution I will denote by X, and what is important for us is that this minimal resolution is a K3 surface. So we can consider the second homology of X. So via Poincare isomorphism, I will really identify the second homology and second cohomology of X. So
Ilya, excuse me. When you say K3, it's algebraic K3. You always assume.
So it's even two polarized K3.
Okay, good.
So it's not, of course, it's not just any K3. It's a two polarized K3, and I will come to this. So we have this lattice H2. So H2 of X is equipped with symmetric bilinear form. And by the way, when I don't mention the coefficient, so I'm writing H2 of something without mentioning coefficients. So the coefficients are integers. So H2 of X is equipped with the intersection form. So this symmetric bilinear form with integer values. And this form is isomorphic to the form, so I denote it by L, and so this is 2E8 plus 3U. So E8 for me is negative definite unimodular form of rank 8, and U is unimodular non-definite form of rank 2. So on an appropriate basis, the gram matrix is for you is 0, 1, 1, 0. Oh, let's put like this. Then we have some special classes in this second homology group of X. So we have the classes of exceptional divisors. So they span root lattice. I will denote by S. And so since we have a unique decomposition of S in this irreducible root lattices, so we can identify this lattice with the set of singularities of our sext. Then coming back to Jan's question, so we have one extra class I will denote by H, so the polarization, so the pullback of a line, and it's a class with square 2, so our K3 is 2 polarized, and we can consider all these classes, so the exceptional divisors and H and the polarization. So they live in the second homology group, and in fact, so they are orthogonal with respect to our bilinear form, the section form. And so this lattice I denote by S. Right? What did I do? Okay, I did something strange. Okay, let me try to reconstruct. So what I will denote by SH is this sublattice generated by S and H in the second homology. So this sublattice is not necessarily primitive, so I will denote S by SH tilde, and the primitive color. And so this is exactly so this is the object I'm interested in. So we have this two polarized hyperbolic lattice. So hyperbolic means that the restriction of the intersection form to this lattice has one positive square. And two polarized means that in this lattice, I fixed an element with square 2, so H. And so this two polarized hyperbolic lattice considered up to polarized isometry, isometry respecting polarization, that's exactly what I will call the complex lattice type of the initial sextic. So to each sextic, for the moment, I didn't assume that my sextic is real. So the only assumption was that I started with a simple sextic. And so out of simple sextic, we constructed this two polarized hyperbolic lattice. And this is what is called complex lattice type of the initial sextic. And well, so if you prefer, you can think about, in a sense, you can think about neuron-Severi group. So if my sextic is very general in its equisingular family, then this SH tilde is exactly the neuron-Severi lattice of our P3 surface. And in any case, even if C is not very general, you can reconstruct S out of this out of neuron-Severi. So it's always the maximal root sublattice in the orthogonal complement of H in neuron-Severi. So these considerations were complex. So now what happens in the real case? So once again, a real algebraic variety for me is a complex algebraic variety equipped with an anti-holomorphic involution. So you can do the construction I presented before in the case of complex sextics. You can do this construction in the real case. So once again, you consider the complex point set of your sextic. You take the double covering of CP2 ramified along this complex point set of your sextic, and you take the minimal resolution of singularities. But if your initial sextic was real, then you get some extra structure on the K3 surface obtained. So you get a real structure. In fact, you get even two real structures. So you can lift the involution of complex conjugation of CP2 to the double covering, to the minimal resolution of double covering. And you can lift this involution of complex conjugation even in two different ways. So they differ by the deck translation of the covering. But if we assume that our real sextic is empty, in fact, one can do the same thing in a more general situation, but for the moment, let's assume that our real sextic is empty. I claim that in this case, I can distinguish between these two lifts. So I need just to choose one of the two lifts in somehow canonical way. And if my real sextic is empty, I can do it. For example, saying that I prefer the lift such that the obtained involution does not have real point, so has empty real path. So one of the liftings, in the case of an empty real sextic, will have empty real path, and the other one will have a sphere of the real path. So it's the sphere is in fact the total space of a double covering of AP2. So let's denote by sigma plus the lifting of the complex conjugation, the lifting to my K3 surface, such that the obtained involution has empty real path. Then I can look at the latest complex lattice type of my sextic, and I can add this additional information. I can add the restriction of the involution induced by sigma plus on the second homology, restriction to SH theory. So now this two polarized hyperbolic lattice, it is equipped with an involution, and once it is equipped with an involution, so the result I call the, of course, once again considered up to appropriate isomorphism. The result is called real lattice type of an empty real sextic. So to summarize, to each empty real sextic, I can associate such a I don't know how do they put it, arithmetic object. So a two polarized hyperbolic lattice equipped with an involution.
Is there a Torelli theorem for families with,
I will come to Torelli Torelli a little bit later ahead of me. But so the Torelli theorem is a statement. So you can treat Torelli theorem in different ways. So in particular, you can interpret Torelli theorem as a statement about construction of holomorphic or anti-holomorphic maps. So in particular, it gives you also information about real objects, not just about complex objects.
Okay.
But indeed, you're completely right. So the global Torelli theorem is a part of this K3 machinery I mentioned in the beginning. So now the theorem. So as I said, theorem is formulated in a strange way. So I will just give you numbers. So I claim that, so it's a theorem we proved with Alex Degtyarev. So I claim that there are 169 classes in this equivariant equisingular deformation classification of empty real sextics. And in fact, they are contained in 159 real lattice types. And this lattice type, real lattice types, represent 139 complex lattice types. But so these are just numbers, but in fact, the true statement is a classification in form of some list. So you can somehow describe in some terms this the classes of this equivariant equisingular deformation classification. So two remarks which are not homogeneous at all. So first of all, before speaking about equivariant equisingular deformation classification, especially speaking about real lattice types and complex lattice types, one can just think about the complex case. In fact, complex lattice types not far from equisingular deformation classification. So, in fact, there is only one, as was proved by Degtyarev and Degtyarev. There is only one complex lattice type that correspond to two equisingular deformation families. All other complex lattice types constitute one connected equisingular deformation family each. So this is the result by Degtyarev and Degtyarev. And as I said, my remarks are not homogeneous. The second remark is the remark I promised. So I'm speaking only about simple sextics, but it's easy to complete the classification of simple empty real sextic to a complete equivariant equisingular deformation classification of empty real sextic, because if you so first of all, as I said, you can treat easily the case of non-reduced sextic, but if you consider reduced non-simple empty real sextics, then it's easy to show that there are only two equivariant equisingular deformation classes. So in this case, so in this case, the only possible singularities are of type, well, it depends how you enumerate singularities. So let's say of type J10, so meaning it's tangency point. So you consider quadratic tangencies of three branches. So if you think about, so that's exactly what happens in the case of sextics. I am trying to describe. So these sextics are unions of three conics, and these conics are tangent to each other at 2 points of type J10. And it's so it's easy to show that this is the only possibility in the case of reduced non-simple empty real sextics, and it's easy to see that there are only two equivariant equisingular deformation classes. So that they are as follows. So one of these conics, so for each such sextic we have three conics. One of these conics is real, and two others are either real or complex conjugates. So this gives two deformation families. So now let me indicate some ideas of the proof of this theorem. So how one can get such an equivariant equisingular deformation classification of empty sextics. So it's as more or less always when one uses this machinery of K3 surfaces. So there is a kind of arithmetical reduction. So one can try to reduce our initial geometric problem to an arithmetic one, arithmetic meaning arithmetic of lattices. And here the reduction is as follows. So coming back to Jan's questions, the statements, in fact, all the statements I will mention below, almost all the statements, so the statements I need to obtain this equivariant equisingular deformation classification. So they are corollaries of the standard machinery. So I need the global Tarelli theorem, so kind of injectivity. I need the surjectivity of the period map, meaning as always subjectivity to the image. So I need the description of the image of the period map. So theorem by Viktor Kulikov. And I also need some results of Sandanat concerning projective models of K3 surfaces. So it really is some standard package used in this type of questions. And then one gets, first of all, a description of complex lattice types. So the description is as follows. So this is really standard corollary of the above mentioned package. So one can describe, this description is not really explicit, as we will see, but nevertheless, in this statement, the description is as follows. So I'm interested in two polarized lattices that represent a complex lattice type of a simple sextic. So for the moment, everything is complex. And the statement is that a two polarized lattice represents a complex lattice type of simple sextic if and only if. So of course, this lattice should be hyperbolic. And of course, it should admit a primitive embedding in L. So L is my standard lattice 2E8 plus 3U. And so that's why I'm saying that the description is not very explicit, because if you have given a two polarized lattice, you should somehow check whether it admits a primitive embedding or not in L. So in the K3 lattice. So this can be done, but it's it requires some work. Then the second condition, so this two polarized lattice should be generated over Q by H, so it's polarization and the roots in the orthogonal complement of H. And there is one additional condition that we should prohibit the existence of certain elements. So we should exclude the cases where there are elements of square 0 and with the intersection 1 with H. Well, so now once we know the standard description of complex lattice type, we can try to go a little bit further and further towards equisingular deformation classification in the complex case. And for this, it's convenient to have a notion of homological type. So for the moment, we had lattice types, so complex lattice types and real lattice types. So what is a homological type? So a homological type is a triple like this. So I have a lattice type, and I consider this lattice type inside the second homology of group of our K3 surface. And so now I have these triples, and I can again consider them up to isomorphism, and this is what is called homological type of our sextic curve. So homological type, of course, knows the complex lattice type, but it's in fact it contains some extra information. It contains the information how this complex lattice type is embedded in the second homology of the K3 surface. Well, so the statement, which is also kind of standard statement, standard application of this K3 machinery in the complex case. So I don't even know to whom the statement should be attributed. So it's not. It was known. It is known. It was used by many people. So the equisingular deformation families of simple sextics are in a canonical bijection with so-called oriented abstract homological types. So what does it mean oriented? So okay, so if we have a homological type, okay, let's say an abstract homological type, so we have such a triple. So we have two polarized hyperbolic sublattice, which is primitive in the K3 lattice L. So we can consider the orthogonal complement of this hyperbolic sublattice. The orthogonal complement has two positive squares, right? Because there are three positive squares in the K3 lattice. I have a hyperbolic sublattice, sublattice with one positive square. The orthogonal complement has two positive squares. This means that if I consider, okay, let's work over R. So let's consider to be able to speak about subspaces. So we can work either over Q over R. Okay, let's do it over R. So so if I consider the orthogonal complement of my hyperbolic sublattice in this real vector space, so this orthogonal complement, as I said, has two positive squares, meaning that each time I consider a two-dimensional plane in this orthogonal complement, such that the restriction of my form to this plane is positive definite, I can, okay, so I have all these two planes, and all these two planes, they can be oriented coherently. So if I have chosen an orientation of one two-plane, so once again, I'm speaking about two planes in the orthogonal complement of my hyperbolic sublattice, and I consider two planes such that the restriction of the intersection form on these two planes are positive definite. So each time I choose an orientation of one of these planes, I get the orientations of other planes, all the other planes. And so what I mean that there are two coherent orientations of this collection of positive definite two planes in the orthogonal complement of my hyperbolic sublattice, and the choice of one of these two coherent orientations is what is called oriented abstract homological type. So oriented means just that we choose an orientation of one of positive definite two planes in the orthogonal complement of the hyperbolic sublattice. And the statement is that this oriented abstract homological types are in the canonical bijection with the equisingular deformation families of simple sex. And so now to get an equisingular deformation classification of simple sextic, one should describe all possible abstract homological types, and they can be explicitly described. So now let's go to the real case. So exactly as in the case of lattice types, so in the case of lattice types, we considered complex lattice types and real lattice types. Now we have a homological type of for each simple sextic, and we can introduce the notion of real homological type. So what do I do? I just add this information to the real lattice type. This information how our hyperbolic lattice is embedded in the K3 lattices. So now I consider such a quadruple, and once again, considered up to isomorphism, such a quadruple is what is called real homological type of the simple sextic. And one can once again use the standard K3 machinery to prove the following theorem. So you can describe real homological types of empty real sextics quite easily. So a quadruple represents a real homological type of an empty real sextic if and only if, of course, the corresponding part of this quadruple is an abstract complex homological type. Then the involution is so we have an involution on our lattice, and so this involution should be skew polarized. So of course, it should be an isometry. Skew polarized means that it sends h to minus h, and so this is just to say that the sextic I am considering is real, and then the fact that my real sextic is empty is reflected in this condition that the invariant part of my involution, so the involution is the involution induced on the K3 lattice by the real structure of my K3 surface. So the invariant part is should be isomorphic to what I denoted by E8 of 2 plus U of 2. So E8 of 2 is just E8 where all the values are multiplied by 2. And the same for U. U of 2 is just U where all the values of this bilinear form are multiplied by 2. And finally, so the theorem we proved with Alex is as follows. So in fact, this theorem is valid in a more general situation than just in the case of empty real sextics. So in fact, this statement works under the assumption that our sextic should be simple, but so real, and I assume that this sextic does not have real singular points. So of course, if my real sextic is empty, I don't have real points at all. So in particular, I don't have real singular points. For this statement, it's important just to assume that there are no real singular points for the real simple sextic considered. And the statement is that in this case, under the assumption that there are no real singular points, real homological type, so this homological information taking into account the singularities, the polarization, and the real structure, so this homological information is enough to determine the equivariant equisingular deformation class. So it's in principle, it's a little bit surprising as a statement because it's definitely not true in general. So it's not true without this assumption that our sextic does not have real singular points. So let me come back before I comment on this statement. Let me come back to this isotopic classification of maximal non-singular sextics. So, for example, this real homological type definitely is not enough to describe equivariant and equisingular deformation classes in the case of sextics, real sextics with one non-generate double point. So this sextics, real sextics with one non-generate double point can be seen as degenerations of non-singular sextics. For example, you can take Hilbert's maximal sextic and look at possible simplest degenerations of this non-singular sextic. And so what can happen with the small ovals? So each of the small ovals in my picture can contract to a point, which gives you, so if you contract one small oval to a point, it gives you a real sextic with one non-degenerate double point. And what can also happen, it can happen then that one of the ovals is glued to another one. So you can see, for example, such a picture. You can get such a sextic. So 5, 6, 7. So this is a possible topology for a simplest degeneration of Hilbert's sextic. And as I said, another option is, for example, like this. It can happen that one of this oval is contracted to a point, and then you have 8 others. It can happen that the exterior oval contracts to a point. So it's clear that the options I mentioned represent different equivariant equisingular deformation classes, but you don't see the difference on the level of real homology type. So the real homology types are the same. But it turns out that if there are no real singularities, then real homological type knows everything about the equivariant equisingular deformation class. By the way, you didn't ask. I have to add this remark. So, in principle, for the moment, I am not allowed to speak about real homological types of real sextics which are not empty, because I define this notion, the notion of real homological type, only in the case of empty real sextics. So the problem could come from the fact that to speak about real homological type, I should add an involution to the complex homological type. And to have an involution, I should have a real structure. And as I said, on my K3 surface, there are 2 real structures. If the sextic I started with was real, and I have to choose somehow one of these real structures. And in the case of empty real sextics, I made this choice. I said that I take the real structure whose fixed point set is empty. So now I am speaking about real homological types of real sextics in a more general situation. But now I assume just that there are no real singular points. And so in this case, once again, I can distinguish between the 2 liftings. So if I have a real sextic without real singular points, this, well, in any case, a real sextic, the real point set of a real sextic divides AP2 into halves. So if you choose a polynomial defining your real sextic, then this polynomial is 0 on your sextic, is somewhere positive and somewhere negative. So there is the positive part and there is the negative part. So these notions are not well defined if you didn't choose a polynomial, because you can multiply your polynomial by -1 and you will switch the roles of positive and negative. But in any case, you have these two parts. One of them, of course, can be empty. But my claim is that if our real sextic does not have real singular points, then exactly one of these halves is non-orientable. So let's choose the other one, and the lifting I will choose to define this real homological type is the lifting such that the fixed point set is above the half of AP2, which is orientable. All right. Once again, I have this possibility to make canonical choice. I have the notion of real homological type, and the theorem tells me that the theorem tells that the real homological type in this situation determines the equivariant equisingular deformation class of our sextic. And so once again, the proof uses a description of period space of simple sextics without real singular points, and having given a real homological type. And so one can once again use this description. So the description, of course, uses some of the global Tarelli theorem and the surjectivity of the period map. So one can play with this period space. So this period space in general has many connected components, but one can show that one can go through the walls, so from one connected component to the other, in this situation when there are no real singular points. So one can go from one connected component to a neighboring connected component, just changing what is called the marking of our K3 surface. So just using an automorphism of the K3 lattice, respecting all the structures we're interested in. And so this is really the key statement in the proof of this theorem I mentioned. So this equivariant equisingular deformation classification. And so I'm sorry, I'm already out of time, even if you said that the time is not limited. So probably I should stop at this point. Thank you.
Yeah. Okay. Thank you. Are there any questions?
Can you write equations for those sextics?
So for some of them I can, not for all of them, but in principle, as you know, this approach where period spaces is somehow orthogonal to equations. So it's difficult to get out of this approach the equations, but for some of these curves I can write equations. So some of these curves have some extra symmetries, and so this allows one to write equations. But I did not try to write equations for all of this. For all representatives, so representatives of all these
equivariant equisingular deformation classes.
I'm just wondering, like in general, if you want to classify, or say, smooth curves, all the types and everything, you can sort of look at this RPN, whatever the number of coefficients you have, and is it anybody studied like how big, say, put some metric on this RPN, like for Bini Studio or something. You can is it like somebody studied like how big those complements of the discriminant are, like in terms
you mean how big are components of the complement of the discriminant corresponding to some particular topological types or isotopy types?
Yes.
Well, there are some results. In particular, there are results by Jean-Yves Changer and Damien Gaillet, and they proved, and then the statement was generalized to higher dimensions also. But they proved for curves that the volume of components corresponding to maximal or close to maximal curves, the volume of these components decreases exponentially fast when the degree grows. So they become really very small.
I'm kind of, the question is oriented towards kind of randomly, because we have now powerful computers, right? So we can randomly, put the coefficient and actually get the full classification if we.
So probably at some moment it will be possible, but up to now, all the attempts I know to proceed in this way led to curves with very few connected components of the real point set. So
it's kind of it's more likely to have an empty curve rather than like the maximal.
Well, not empty, but so with really small number of components. So empty is this is also this. So empty curves, so empty non-singular curves, they just form one connected component of the complement of the discriminant.
But it's a big component, or is it?
It's well, it's relatively big, but still, if you pick coefficients at random, I guess you will see some connected components, but you will see very few of them.
All right, thank you.
Okay, more questions?
Yes, I do have a few questions. So I'm not very familiar with the language. So when you talk about the lattice type.
Okay, Ilya, I have to apologize because I have to go. So then,
Thank you for invitation.
So when you talk about the lattice type, so first the lattice assume that it's a free abelian group. You also have symmetric, not degenerate, but integer valued by linear form.
Yeah. I use this terminology later. So it's a free abelian. So here is free abelian group of finite rank equipped with a symmetric bilinear form, integer valued form. Yeah.
It does not have to be not degenerated, or does it?
Well, in principle, so the lattices are not necessarily non-degenerate.
Also, notice there is there could be possibly a zero form. That's always And my second question, that's about the lattice type. And when you talk about the
but I'm sorry, but in fact the lattices I was speaking about, they will all, so this non-degeneracy condition was always satisfied.
Yeah, I noticed that you have the Deacon diagram,
for example, for complex lattice type. So in fact, so what is this hyperbolic lattice? So it's a root lattice. Right?
So for example, the E8 too, assume that the E8 root lattice, but you have the bilinear form multiplied by 2.
Sorry?
So the E8 too on this slide.
E8 of 2, it's still not degenerate.
Yeah. So that the abelian group is the root lattice, but the root lattice has a invariant bilinear form. Let's say they're coming from a Killing form, but
Yeah.
So with the length of each root, assume that it's a square root of 2. So
Yeah.
and so in this case, you multiply this bilinear form by 2,
But
right?
So E8 of 2 is, I just multiplied E8 by 2. So it's just the values. I just multiplied the values, all the values by 2.
Okay, so
it's no more a root lattice. There are no roots at all.
Well, it depends on that. I mean, the abelian group is always this isomorphic, but the
abelian group is still the same. The form is different here.
That's right. The bilinear form is changed, but
yeah, I just multiplied the bilinear form by 2.
And what is the U here? I'm not familiar with the lattice U.
U is just well, sometimes it's called hyperbolic plane, but this terminology is confusing. So it's rank 2 lattice with the Gram matrix with an appropriate basis 0, 1, 1, 0.
Okay.
Like this.
So the rank of all this lattice is always the rank of the second homology group of this.
Well, the total rank of so the total rank of L is 22. Yeah. So the rank of L is 22. So L is so in one of the ways to describe
L is always 22 or 20.
Yes. L so the second homology of our K3 surface is of rank 22.
Always. Okay.
So this K3 lattice is always, so it's the K3 lattice, so it's isomorphic to twice E8 plus 3 times U. Okay. Another way to describe this lattice, it's a unimodular even lattice. So even that all the squares are even.
That's
unimodular even lattice of signature 3 or 319. So 3 positive squares and 19 negative squares.
Okay. So not necessarily positive definite.
No, it is not. It is not positive definite.
That's good.
It's always of this. It's always isomorphic to twice E8 plus 3 times U, though this decomposition is not canonical.
And then also on this abstract complex homological type. So here you have this H tilde. I wasn't quite sure. H tilde is also a sublattice. Am I correct?
Yes, SH tilde is just the primitive hull of the sublattice generated by exceptional divisors and the polarization. So if I consider this sublattice generated by the exceptional divisors in our minimal resolution, and the polarization, the pullback of a line, then this lattice is not necessarily primitive in the K3 lattice. So
I see. So in this data,
it's not, the quotient can have torsion. So what I'm taking the primitive hull.
Okay. So you also have a specific vector H, and for the
yes, I have several specific things coming together with my sextic. So since my sextic is singular, I have in my K3 surface these classes of exceptional divisors. And since my I start with this sextic curve, I have this lifting of a line. So I have this special class, this polarization. This is exactly what Jan was asking. So my K3 surface is a 2 polarized K3 surface. So I have this polarization with square 2, this class which is given by the pullback of a line.
Do you have any requirements for what the H should be? Say, for example, the length or whether that's isotropic? Or...
No, so it depends. What do you mean by requirements? So if you, So it depends what are the structures you fixed already. So if you just look at the K3 lattice, then you can pick any vector of square 2. This will be good for this polarization.
So the H has to have you said that
it's of square 2. So
square 2. Okay. So this is that H product with itself is 2.
Yes. So square meaning in the sense of this bilinear form. Yeah.
Okay. Good. Yeah, that's what I was asking. Thank you very much. I really appreciate it. And I'm not familiar with this algebraic geometric interpretation, but this lattices appear with such a structure appear in vertex algebra. Lattice vertex algebra. That's why I was asking.
Yeah. Thank you very much for the questions.
We actually also have a question in the chat. And thank you for the interesting talk. Is there a document available yet?
If by document you mean the notes of this talk, the notes are available. So I send them to Jan. If you are speaking about the paper, so we are writing a paper with Alex, but the paper is not yet available. So it will probably, it's also a dangerous phrase, but I hope this paper will be available soon.
Thank you. Are there any more questions?
Can I just to clarify? So if it's smooth empty, then there's just one.
Yes.
One thing.
Yes.
And this is like in any degree.
It's in any even degree. So to have some empty curves.
I mean, in here your SH would be just H, right?
Yes, of course, yeah, because there are no exceptions.
Okay. Yeah. But this statement is true for any degree.
The statement is true in any degree. So for empty non-singular curves, everything is simple.
Right. Thanks.
More questions? If there are no more questions, then let's thank the speaker for a great talk. And that's the end of the seminar.
Thank you very much.